During flight, an airplane's wings aren't still. They bend, they twist, they lift several meters upward. And although it seems impossible from the outside, that's not a flaw. It's precisely the reason they don't break. It's not the engine, it's not the pilots, and it's not just the strength of the metal. It's something happening inside the wing itself. Silent, constant, invisible. And if it ever stopped working, the wings of an airplane like the one that crossed the Atlantic last night would bend upward and break in a matter of seconds. How is it possible that millions of flights have crossed the planet without that happening? The answer is one of the most important engineering lessons in the history of aviation. In this video, you'll discover why an airplane's wings can bend several meters without breaking, what tragedy forced a complete redesign of modern aviation, and why engineers don't try to prevent wing damage from occurring. They try to find it before it becomes dangerous. And when you understand how this system works, you'll see airplane wings in a completely different light. To understand the problem, you first need to understand what a wing supports on each flight. A typical commercial airliner, say a fully loaded Boeing 737, weighs between 65 and 80 tons. All that weight hangs from two wings, just two. And those wings don't just support the weight of the plane on the ground. During flight, the forces acting on them are much greater. When the plane takes off, the wings literally lift that weight from below. But when the plane encounters turbulence, when it maneuvers, when it flies through a storm, those forces can double, triple, or even more. Engineers call it the load factor. And under extreme conditions, a commercial wing must be able to withstand forces equivalent to 2.5 times the total weight of the aircraft without breaking, without permanently deforming, without failing. Now imagine that applied to the wings of an Airbus A380. An aircraft that can weigh more than 500 tons. How do you build something capable of withstanding that? The most obvious answer would be to think that wings are strong because they are rigid. But it's just the opposite. If a commercial wing were completely rigid, it would be much more dangerous. Inside, a wing isn't a solid piece of metal. It's a structure designed to distribute forces across the entire wing, preventing them from concentrating at a single point. But for decades, engineers faced a much more difficult problem. Wings aren't rigid. They can't be. When an airplane flies, the wings bend upward, not just a little, quite a lot. On a Boeing 787, the wingtips can flex more than 7 meters during normal flight. 7 meters. And that's not a flaw. It's exactly what's supposed to happen. A completely rigid wing would be a wing that breaks. Rigidity doesn't absorb energy, it concentrates it. And when it concentrates too much energy, it gives way. But here's an even bigger problem. That flexibility has a very precise limit. Too much rigidity and the wing breaks. Too much flexibility and the wing loses its aerodynamic shape, stops generating lift properly, and the airplane loses control. The margin between these two extremes is surprisingly small, and keeping the wing within that margin for decades, enduring thousands of flights, storms, turbulence, and extreme temperature changes became one of the greatest challenges in aeronautical engineering. And the solution came from an unexpected place. Because the key wasn't making the wings stronger, it was making them smarter. For a long time, airplanes were built almost entirely of aluminum. Aluminum is lightweight, relatively strong, and easy to work with. But it has a fundamental limitation: fatigue. Every time a wing bends, the metal suffers. You can't see it. You can't feel it from the outside. But at a microscopic level, the metal's crystalline structures gradually fracture, and with enough flight cycles, these microfractures accumulate, grow, and eventually the metal gives way. This phenomenon has a name. It's called metal fatigue, and in the 1950s, it killed people. The de Havilland Comet was the world's first commercial jet airliner. It was revolutionary, it was sleek, and it had square windows. That was the problem. The square corners created stress concentration points in the fuselage structure. With each pressurization and depressurization cycle, the metal around the corners fatigued faster than the rest. 3 Comet airplanes disintegrated in flight in less than 2 years. More than 100 people died. That tragedy forced a complete rethink. And when engineers began searching for solutions, they discovered something that would change aviation forever. Aluminum wasn't smart enough. They needed materials that were not only strong, but also responded predictably to repeated forces. Materials whose fatigue was controllable, measurable, and manageable. And this is where the system that makes it possible for modern wings not to break comes in. It all started with a combination. Not a single material, but an architecture of different materials working together. Engineers began using increasingly sophisticated aluminum alloys. Then came composite materials, carbon fibers embedded in a resin that holds them together. The result is a material that, in proportion to its weight, is stronger than steel, doesn't corrode, and whose fatigue behavior is completely different from that of metal. In a metallic aircraft, a microfracture grows, it advances, it spreads. In a composite material, the fracture stops. The fibers block it. The energy is dissipated in a distributed manner instead of concentrating in a single point. That's what makes longer, thinner, lighter, and stronger wings possible. The Boeing 787 uses composite materials in more than 50% of its structure, including the entire wings. And those wings withstand load tests where they bend upwards more than 7 meters before the engineers stop them. Not because the wing has failed, but because they've already proven what they needed to prove. And the most surprising thing is that one of the systems that helps protect the wing wasn't even originally designed to protect it. But the materials are only half the story, because there's another system working in parallel that very few people know about. Inside the wings of modern airplanes, there's not just structure. There's fuel. An airplane's main fuel tanks are in the wings, not in the fuselage. In the wings. And that's not accidental. The fuel inside the wing acts as a counterweight. When the wing bends upward due to lift, the weight of the fuel inside it acts in the opposite direction, reducing the stress on the wing root, the point where the wing joins the fuselage. Without that weight, the forces at the wing root would be much greater. The wing would need to be significantly thicker, heavier to withstand them, and that would make the airplane less efficient. So, fuel doesn't just propel the airplane, it protects it. Now there's a moment in flight where this becomes especially critical. At the end of a long flight, the airplane has burned thousands of liters of fuel. The wings are almost empty. The stress at the wing root increases. The airplane is, quite literally, in its most vulnerable configuration just when it needs to land. That's why in-flight refueling procedures aren't just logistics, they're structural engineering. And there's something else that happens in the wings that most people would never imagine. Because the real challenge isn't surviving one flight, it's surviving 30,000. 30,000 takeoffs, 30,000 landings, entire decades of fatigue slowly accumulating. With the temperature changes between ground level and cruising altitude, the wings contract and expand. Aluminum and composites respond differently to these thermal changes. And the structure has to be designed so that this difference doesn't create additional stresses that lead to fatigue. Furthermore, every wing component has to be monitored. Modern aircraft have sensors distributed throughout the structure that detect vibrations, deformations, and changes in structural stress in real time. The data is sent to the aircraft's structural health monitoring system. If something starts behaving unexpectedly, the system records it. It doesn't wait for something to break, it detects it beforehand. And here's the truth most people don't know. Engineers don't expect a wing to remain perfect forever. They assume damage will eventually appear. The entire philosophy of modern aviation is about finding it before it becomes a hazard. The difference is enormous. In early all-metal airplanes, failure came suddenly, without warning, without any sign. The microfracture reached a critical size and the structure gave way in seconds. Modern aviation learned from those tragedies, and it completely changed its design philosophy. Today, a commercial wing is built with what engineers call damage tolerance. This means that even if a crack exists in the structure, the wing will continue to operate safely long enough for technicians to detect it at the next inspection. Maintenance checks on a modern airplane are calculated with surgical precision. Every certain number of flight hours, every certain number of pressurization cycles, there is an inspection. And these inspections don't look for if something is broken. They look for if something is starting to break. That's what keeps the wings intact. Not just the materials, not just the design, but a complete system of monitoring, maintenance, and engineering philosophy that treats time as the enemy and early detection as the only defense. Because behind every wing are decades of lessons learned, many of them paid for with tragedies. There are materials that are not only strong but also distribute forces intelligently. There is fuel that acts as a structural counterweight. There are sensors that monitor the wing's health in real time, and there is a design philosophy based on detecting damage before it happens, not after. Wings aren't rigid. They are flexible and resilient at the same time. They aren't eternal. They are designed to travel long enough before needing attention. And that combination is what makes it possible for an airplane to cross the Atlantic at night with hundreds of people on board, without anyone on board thinking for even a second about whether the wings will hold. There's something I find profoundly fascinating about all of this. Modern aeronautical engineering isn't striving for perfection. It's striving for predictability. It doesn't want structures that will never fail. It wants structures whose failures are predictable, detectable, and manageable before they become a real problem. It's a way of understanding safety that goes far beyond airplanes. The next time you look out the window during a flight and see the wing move with the turbulence, remember this. You're not seeing a structure about to break. You're seeing a structure designed precisely to survive it. If you found this interesting, I've included another video on screen that I'm sure will surprise you.